Okay, thanks, Miriam. So everyone can hear me fine? Okay, great. This is a little awkward. I can't actually point at those slides, so I'm going to just try to do my best to point at things that I want to point at the slides. Okay, so today I'm going to tell you about off-policy learning, and these lectures are sort of long. You know, an hour and a half is a long time, so I want to treat it a little bit more like an actual lecture. I want to make it as interactive as possible. I know it's sort of hard for you guys to ask questions because you don't all have microphones, but I'll still try to get you to ask as many questions as you can along the way. I'm going to give exercises, which is maybe a little non-standard, to sort of give you mental breaks as we go along. And I want to mention, too, is that this is sort of synthesizing a story around off-policy learning. It isn't exactly written down anywhere, but we are in the process of writing it down. So if you want to know more and get more references for this stuff, we're going to be putting up a paper on archive really soon. Should have been this week, but probably next week. And the only thing I want to mention is by the end of this, I hope that you will know something about what our goals in off-policy learning are, what the key challenges are, and then what some of the things we have done in terms of algorithmic development to meet those challenges. And I'll mention one other thing. I have a tendency to start speaking fast, so also feel free to interrupt me if that happens. Okay, so like I said, I want to sort of get these key concepts across. So what I'm going to start off is just by telling you what is off-policy learning. So you've sort of heard a little bit about what it is from Rich. It's you have a different behavior policy mu that's different from the target policy pi that you care about. So you want to evaluate some other target policy pi, and here's an example both for policy evaluation and control. So you might imagine you're an RL agent, you need to control some energy storage. You need to decide how much energy am I going to store in my battery, how much am I going to discharge from my battery. And, a company may not just want you to run whatever policy on such a system. So you might imagine you have a trusted policy, say engineered by someone, and now you might want to ask, well, what if I were to run this other policy that a new person has proposed? And you want to get a sense of, is that a good or a bad policy? So your behavior policy is different than the target policy you want to evaluate. And then in another case, you might say, I'm going to run my current policy, so my default policy, but I'd like to know what would have been the optimal thing to do. So that's an off-policy control. And I'm going to emphasize here that we don't have access to the true model. So here I'm just going to be imagining that we're only ever having access to a stream of data. Okay, so this is off-policy learning. It's a very simple idea. And in this talk, I'm going to focus on policy evaluation, but there's a lot of interesting questions in control as well. Policy evaluation is the place to start. There's already a lot of interesting questions. Okay, so again, these first few slides are mostly going to be laying out what is our problem setting and what is some of the notation. So this is mostly going to be all the notation I'm going to use. I'm going to try to keep it as simple as possible. You've already heard about what policy evaluation is. You know, we want to learn our values, and you've seen it presented in many different ways. I'm going to present it again in a slightly different way in an effort to try to show the minor differences we're going to put into our objectives when we look at off-policy learning. Okay, so our goal is going to learn our values. Our values are still defined as the expected return, discounted return into the future, expected cumulative sum of rewards into the future under some policy pi. And I'm going to write this as a goal like this, where we would like the expected value of this TD error. The TD error is defined at the bottom. I'm not going to point at that. So the TD error is defined at the bottom. What's the reward plus gamma times the value in the next state minus the value at our current state. You're comfortable with the TD error. So we would like to make the expectation of the TD error 0 across all states, weighted by some distribution D. Okay, and this D I'm leaving intentionally vague right now because it's the thing that's going to change when you look at off-policy learning. Okay, so that's going to be our goal. You can imagine for yourself that your goal is still to make the temporal difference learning expected TD error 0 in all states. And here I'm just summing this all up so that you can write it as one value that's a scalar value rather than a vector of values. Okay, in linear value function approximation, this is going to change just a little bit. So the first one is sort of how we write it for a tabular setting. For linear value function approximation, we're going to assume our value function is linear in some features of state. Okay, so here x of s is going to be dot product with some weights w, and our goal is to learn those weights w. Okay, and I'll mention again that most of this talk is going to be about linear value function approximation. And at the end, I'll tell you how all your understanding is going to apply to nonlinear function approximation. So, you can be okay with the fact that we're only talking about linear function approximation for now. Okay, so then the criteria changes a little bit. The criteria is now that we still want this expected TD error to be 0, but notice there's also these extra features, x of s there. You can sort of mentally imagine that that's the gradient of the value function that we usually think of when we derive this TD update rule. But for now, I'm just going to get you to believe me that that is our goal. Okay, so when we were trying to find our value function, in the tabular case, it was the first line. And when we move to linear function approximation, our goal is going to be to get this equation to be 0. Okay, so hopefully all the notation on the slide is clear. We have a feature vector that is defined on states, and we have our TD error. And whenever I talk about random variables, they're going to be uppercase. So S, A, S prime are all uppercase because we're taking expectations over them. And they'll be lowercase if they're instances. So here I have S is equal to little s to emphasize that S is actually a specific state that we're talking about. I'm also being a little pedantic by having delta be explicitly a function of S, A, S prime, just to be really clear what we're taking an expectation over. Okay, so delta is random, and X of S is random. So to expand out this expectation just a little bit, when I say the expectation of the TD error, then we have to sum over all possible actions and next states that we could see according to probabilities pi and p. And I'm subscripting with pi just to be clear what distribution we're following, because we're going to have a mu and a pi. Okay? So this is, again, mostly all the notation we're going to look at, and so that should hopefully be clear. If there's any questions on notation, do ask. Okay, so in the on-policy case, I've told you what our goal is. In the on-policy case, we usually use temporal difference learning to find the solution to this problem where we get this left-hand side equal to the right-hand side being 0. And so the temporal difference learning update looks like take your weights from the last time step and adjust them in the direction of some step size times delta times xt. Hopefully you have all seen the TD update rule, if not today, before then as well. Okay, so you can kind of see how these two things are related to what I wrote on the last slide. If we look at the expected value of delta t xt, that's actually what is written just a little bit more complicated with the delta of S, A, S prime, and X of S. Okay, so the thing I wrote on the last slide is the expected TD update. And, you know, when we get to the point where the TD update is 0 summed across all states, we've reached this point where an expectation, we should no longer be updating, so we're going to stop changing our weights. Okay, so we've reached this fixed point or the stationary point where we're no longer have a direction that tells us you should change your weights away from this point. So that's sort of why temporal difference learning is actually solving this goal, because whenever we imagine delta t xt and expectation is 0, then we've reached this fixed point. Okay, good. So we're going to keep seeing this equation over and over again, the sum of d of s over states. So if you find it at all confusing, now is a good time to ask. Okay, good. So, oh, good, you have a question. Good. It is a good point. Like I said, I kind of just pulled it out of nowhere. Right now, I'm giving you the intuition that we want that goal because of the TD update. We know TD is trying to get to this fixed point, and this looks like the expected TD update. So if our expected update is 0, then we've reached a fixed point. So that's the intuition, but actually it does come from writing down what the Bellman operator is, which I was going to show more later in the talk. But if you look at this original, the one in the tabular case, delta is actually equal to r plus gamma v of s prime minus v of s. In expectation, if that is 0, then you have your TD fixed point. Because the first term is the t times v that Amir Masood just described, and the second term is your v of s. So in expectation, if that's 0, you're at your TD fixed point. And the TD fixed point just looks a little different once we move to function approximation, which I'll explain just a bit more later. Okay, so in the on-policy case, we know how to find the solution using temporal difference learning. And I would just leave it as a question for you to get you to be tracking for yourself what other algorithms you know of at this point now that could be used to try to find this fixed point solution. I'm not going to actually answer that question. I just feel like along the way it's good for you to have questions to answer for yourself. So for example, LSTD is one, that least squares temporal difference learning is one Amir Masood mentioned, and you could think of others. I'm going to focus on temporal difference learning. And now we can ask, how does this change for off-policy learning? So this has all been the on-policy case. Okay, so what happens in the off-policy case? There's going to be two modifications. So now instead of taking your policy pi, running your policy pi in the world, getting a bunch of samples of rewards, and then using those to estimate your value function with temporal difference learning, we're going to be running some other policy mu. Actions are going to be selected to it, according to it, and now we're going to have two differences. So one thing is that from this state, we're going to take an action according to mu, and now that's going to give us what the TD update is for mu, but it's not going to give us the TD update for pi. So of course, we would like to know from the state, what is the TD update for pi instead of mu? Okay, so we're going to have to adjust for that thing. And the other thing we might imagine is if we ran pi, we would actually see different states S at a different frequency. Okay, so, you know, mu might choose to stay in one part of the world, and pi would have actually gone more often to a different part of the world. So we actually would see the state that we're doing our TD update from at a different frequency. So these are the two really key distinctions when we move to off-policy learning. And I'm going to highlight these two distinctions right now and sort of how we address them. Okay, so how would we address point one? So the first point is really about adjusting the action probabilities. Okay, so this actually is not going to be that difficult to deal with. We're going to generate data from mu, and then we can still get an unbiased TD update for pi just by using importance sampling. And I'm just going to step you through a few of these lines that show you really how simple this idea is. If you've seen importance sampling before, this will be really obvious. And if you haven't, then you're going to be introduced to importance sampling, which is a really nice tool. Okay, so I mean, imagine we started off with the goal that I've said before, the delta times x. We want this expected value under pi. I'm just going to start expanding it out. So the first line is just rewriting the definition. So it's still just the expected value of delta times x. And now I'm just going to add one extra term, which is a mu divided by mu. That's just one, so there's no trouble with just adding that into that next step. And then the third line, the third equals, I'm just going to bring mu and pi inside the second sum and look at the ratio between pi and mu. Okay, now what you're going to notice on this second to last line is that we have an expectation that actions are chosen according to mu, and states are still, of course, chosen according to the dynamics in the underlying world. And now we just have this extra term in front of the delta. So now we have this pi divided by mu times delta times x. There's no fancy math here. There was just a multiplication by 1, and they're just moving a few things around. Okay, and this is called the importance sampling ratio, pi divided by mu. And so what we're really left off with is, if we would like to get an estimate or an estimate of the expected value of this delta times x under pi, then we could actually have sampled according to mu and just multiply by these importance sampling ratios, and we're going to be able to estimate the same value. Okay? So the result is we have an off-policy TD update that says instead of doing step size times delta times x, we just have to add this extra importance sampling ratio in front, and that's going to adjust all our action probabilities for us. And it's going to be like we had sampled from expected value under pi. Okay, so that was easy. Obviously, if this solved the problem, then we'd be done now, and we could all just go and eat early. But there's going to be a lot more problems. But in either case, this is one way to address the action probabilities problem. Okay, and let's talk about the second point. So the other way that off-policy learning is different is that we also might care about adjusting the state probabilities, not just the action probabilities. Okay, and I'm going to give you an example of when these two things might be different. Okay, so again, imagine that your behavior policy is mu, it's running around, and it's going to visit states at different frequencies. And I'm going to call the state visitation function d mu. So it says that is a function from states to 0 and 1. It just tells you what is the probability that I will be in this state if I were to run around the world forever. Okay, so this is usually called the stationary distribution, but for simplicity, you can just really think of it as state visitation. Okay? So in this example, look at this little world has, the start state is the white box in the middle, and then you can either go left and see green, or you can go right and see blue. Okay, and if you choose to go left, then you just have to go left all the way until the end, then you can come back to the white, and if you choose to go right, then you have to go all the way through the blue and come back to the white. Okay, so if mu chooses left with probability 95%, then it's going to be in the green part of the world most of the time. And if pi chooses left with probability 20%, then it's going to be in the blue part of the world most of the time. Okay, so this means that when we actually sample states, the states that we will see under mu are going to be quite different in terms of how frequently we see them compared to the states under pi. Okay, makes sense? And now, so for d mu in this case, the green side would have high probability, and on the blue side would have low probability. The states on the blue side would have low probability. I hope that makes sense what the state visitation is. Okay, so this is just a second point about there being a difference, but it's not clear it's actually a problem. You know, adjusting the state action probabilities is clearly critical. We can't just take what the behavior policy did and assume that's going to tell us anything about the target policy without adjusting some of the action probabilities. Here, maybe it doesn't matter so much what states we start from. So I'm going to leave it as a point of difference, and I'll tell you later why it does or does not matter. Okay, so really the summary, the goal here was just to introduce you to what is the off-policy learning problem and how is it different from the on-policy learning problem. And now we're sort of going to start more into what the rest of the content is. So really the off-policy learning is different in these two key ways. We have to adjust action probabilities are different and the state probabilities are different. We sort of saw one simple solution at least to adjust action probabilities with importance sampling. And many of the algorithms do use importance sampling as a strategy. Okay, and now the rest of what I really want to go through is, now that you know what off-policy learning is, why should you care? So why is off-policy learning an exciting topic? How do we address point 2, which I didn't tell you how to do, and should we address point 2? And this is going to be all about what are the different objectives we care about in off-policy learning. And then the last one, of course, is now what are all the algorithms we're going to use to actually solve these objectives? Okay, good. Okay, let's start off with why is it important. So actually, Rich sort of motivated a bit why it's important, but I'm going to give a little bit more motivation about why I think off-policy learning is sort of one of the key questions for AI, and we're really going to need good off-policy learning algorithms to get general intelligence. So I've listed safe reinforcement learning as one of the reasons it would matter. I don't know a lot about safe reinforcement learning, but I do know that from the example I gave you earlier that it is common, I think, in an industrial setting that you would like to run some default policy that you trust, and then actually answer questions about many other policies. So actually, Mohamed's going to say some nice stuff about that later. So safe reinforcement learning is sort of a more obvious setting where we'd like to do off-policy learning, but that's really a single behavior policy, single target policy setting. There's really a whole lot more that we can do with off-policy learning that maybe isn't as obvious. So the two things are what-if questions and predictive knowledge. I'm going to explain to you a little bit about what if questions are, but both of these fit into this idea of general value functions, and we're going to need off-policy learning to learn general value functions. So I'm going to say what if questions are, and then the other reason you might care is about options. So I'm not going to tell you anything about options because Doina Prekop is going to tell you all about options tomorrow or the next day. But if you've heard about options, then maybe you're excited that off-policy learning is going to be helpful for those, and otherwise options are fabulous. So it's good to develop algorithms for them. Okay, so I'm going to say a little bit about why off-policy learning is important, specifically to help us answer what-if questions. Okay, so what are what-if questions? They're exactly what they sound like, actually. So we get to have one stream of experience. Of course, I only get to behave one way in my world, but I want to ask questions about other ways of behaving. Okay, so I want to ask, what if I had done something else? They're called what-if questions because I want to know what if I had done something else. So going back to the example with an agent that charges or discharges energy in a battery, you might want to ask, well, I'm currently taking a sort of conservative policy for charging and discharging. What if I were to more aggressively discharge energy from the battery until energy prices were low? Okay, so, for example, I'm going to ask what would happen if I ran this other policy until some important event occurred. So that's different than the way that I'm behaving. Or you might want to ask, I'm driving my usual way to get home. Would it be nicer to take a detour through the park? So what if I went and did this other thing? Okay, and then one that's maybe a little less obvious, something like how long will it take me to get to the store is often a question we ask ourselves. And again, you might just be walking somewhere and you might say, what if I were to start going towards a store? How long would that take me? Okay, so all of these really are what if questions, and we're asking what if questions all of the time. So I don't think I have to motivate what if questions too much, but I'm going to motivate why value functions are useful to answer what if questions. And I feel obligated to give one slide about why we have to ask what if questions, because we have one stream of experience. So what if we only need to ask these off-policy questions because we can't actually go execute all the different things we would like to do on policy, and that comes from having the situation where we have one stream of experience. So there are newer methods that do asynchronous learning where you go and you instantiate multiple instances of the environment and you learn from data gathered from multiple instances of the environment. So that's different than having one stream of experience. Those methods can be very helpful for actually training policies faster, but they are sort of restricted to certain settings where you have simulators and aren't necessarily applicable to the general AI setting. So I really want to motivate that asynchronous methods can be helpful, but aren't necessarily going to be part of the solution for general AI, and we are going to be able to ask these off-policy questions. Okay, so again, we have one stream of experience. Now, how can we actually use value functions and off-policy learning to answer these what-if questions? Okay, so the idea really is what-if questions are always policy contingent. So you're asking, what if I did this other behavior, if I behave according to policy pi, and our value function tells us something about what happens into the future if I behave according to some policy pi. So value function, by definition, is this expected discounted cumulative sum of some signal into the future. Okay, and that signal doesn't really have to be the reward. It could be any signal that we find interesting about the world. Okay, so there's been this really nice generalization recently to say we can have general value functions where the signal doesn't have to be the reward. It can be any cumulant, so the thing that you're going to accumulate into the future. And we can have discounts that are state dependent. Okay, so you should really go look at this paper to see all the different things that general value functions can do. But they're a very expressive language for what-if questions. And I'm not really going to be able to go into depth about them, but I'm going to give you one example that sort of gives you a flavor of the types of questions that can be asked. If we can answered if we can actually get the value functions for these general value functions. Okay, so let's go to this question about how long will it take me to get to the store. Okay, so let's imagine you have a policy that says that is able to get to the store. You have a cumulant CT plus 1, that's 1 everywhere. Yeah, it's going to feel a little weird because remember the cumulant is no longer the reward. It's not something you're trying to maximize. It's just some signal that you have specified. Okay, and then you have a discount that's 0 when you reach the store and else it is 1. Okay, I'm going to show you what that means. I should do that. But when the discount is 0 when you reach the store, that's really indicating termination and that you've reached the end of something. Okay, so what would the value function for something like this look like, where you have this policy, cumulant, and discount I just described? Okay, so the value function is still like it usually is. We still have our immediate reward, or cumulant in this case, plus gamma times value on the next state. Okay, so here you might imagine that you're going to see 1 no matter what. The cumulant is always 1. And probably after one step of executing your policy of the one that tries to go to the store, you're not going to be at the store yet. So your gamma is still going to be 1. And so you're going to bootstrap off of your value on the next state. Okay, so just expanding this out a little bit more, you're going to have a cumulative 1 plus gamma times 1 again. And then again, you're going to see, did I reach the store yet? Okay, and these discount factors are going to start multiplying each other. So we have gamma t times gamma t plus 1. If you go back to what you're used to, where gamma is a constant, you can think of this as gamma and gamma squared. Okay, so we're always discounting more into the future. These discounts are actually accumulating as time passes. So the second time here that we discount, we're saying, did we terminate one time step ago? Did we terminate on this time step? And that's going to keep accumulating. Okay, so as soon as gamma t is equal to 0, this is going to end this accumulation, and you're going to stop accumulating anything after that because your gamma t's are always going to be multiplying in, so you're always going to be multiplying in at 0. Okay, so then what is the answer to this question going to look like, actually? It's going to say, once I reach the store, I will have added up CT plus 1, which is a value 1, the number of steps that it actually took me to get there. So the answer to this is going to be, how many steps did it take me until I actually reached the store? Okay, so just by specifying a policy, a cumulant, and a discount, and then going and approximating the value function, the answer to the value function, so that this value function estimate lets us answer how many steps until I can actually reach the store. Does that make sense? Does anyone have any questions about that? So sort of the cool thing is that this language can be a little overwhelming, actually, because how do you specify the policy? How do you specify the cumulant? How do you specify the discount? But really the point here is that it's a very expressive language that lets us ask a bunch of what-if questions about our world. And then it does let us have, both those questions are powerful and they are going to need off-policy learning. Yeah, sure, go ahead, Mirasood. Yep.
You could also model this as an episodic curve.
Yes.
So what is the benefit of formulating the more general?
If you were more comfortable for defining a general value function where you said, I'm going to just going to generalize in terms of cumulants, and I'm still going to use an episodic formulation to tell me when I terminate or not terminate, that's actually no problem. You can still use standard methods to estimate the value function. But sort of the nice thing about having a state-dependent discount is it does let you kind of talk about episodic or continuing with the same language. So it lets you write down one language to sort of encompass a larger body of problems. Okay. Oh, go ahead. Great question. So what I should have written here is that C is really the same as the restrictions on C are the same as the restrictions on the reward. It's going to be a function of state, action, and next state. And so here it happens to be 1, so it's trivially a function of state, action, next state. It's a constant function. But yeah, it definitely cannot be dependent on time, and either can gamma t. Gamma t also has to be state dependent. So here I've already sort of starting to introduce looser notation. But actually, this will be really the only slide where we sort of see these general ideas for GVS. Great question. Any other questions? Okay. So GVS are this nice language, and we are often going to specify policies different than our policies. So we're going to need a good off-policy learning algorithms to actually learn all these general value functions. Okay. So hopefully that's one way maybe you haven't really thought about how off-policy learning could be helpful for whatever setting that you are considering, and maybe realize a little bit that what-if questions could be a helpful way to do training. But what I'm going to do is give you one of the first exercises to give you a chance to sort of think a little bit about all the things I just talked about. And I'm going to give you maybe 2 minutes because we're not going to have that much time. I have lots of things I want to talk about. But I'm going to give you 2 minutes to turn to the person beside you and just talk to them a little bit about what thinking about off-policy learning in this way means to you. Is there a setting you can think of that you're working in right now where you might actually want to answer questions about a bunch of different general value functions? Go ahead, turn to your neighbor, talk for 2 minutes. I'll be timing you. Okay, I'm going to have to interrupt you guys. This is the terrible thing about having such a time limit. You're right in the middle of a discussion. So table the thoughts that you just had, and hopefully you'll keep discussing with the person beside you after. 2 to 3 minutes is just not enough for discussion, but such is life. Okay, so really, my goal here was just to get you start thinking a little bit about how could you use off-policy learning. Hopefully you've thought for yourself how you personally might use off-policy learning or research questions you think are interesting. And now let's finally move on to the question of how are we going to actually learn value functions or general value functions off policy. And this is where we're going to come back and revisit the question about how do we adjust state probabilities and in general what are our algorithms going to look like. Okay, so again, I'm always going to start off with what does the on-policy thing look like and then contrast it with what does the off-policy thing look like. Okay, so first I'm going to write down the simplified variant of the mean square projected Bellman error. I think the mean square projected Bellman error has been stated already, but it is the objective that is being optimized by TD, though TD is not actually a gradient rule on the mean square projected Bellman error. But here I'm just going to write this formula that I told you would see over and over again. Again, it's still this expected TD error times the features weighted by some distribution D. And here the distribution on the on-policy case is d pi. Okay, and then this is actually a vector of values if you notice, because you have a delta, which is a scalar, times a feature vector, which is of size, let's say you have k features. This is k-dimensional vector. So the expected value of that thing is still a k-dimensional vector. And we want this whole thing to be equal to the 0 vector. Okay, so just to write that down as one scalar objective, we're going to take the 2 norms squared of that and then ask that we get this objective as small as possible. I'll mention that I'll give you the full mean square projected Bellman error later, but this is a simplified variant simply because I'm not including this covariance matrix, which really doesn't matter a whole lot anyway. The most important part of this mean square projected Bellman error is this term here with the sum over d pi expected value of delta times x. Okay, so what is this objective actually saying? It's saying I want you to go and get reduce the expected TD error times x, assuming I'm actually starting in states S. So my pi is running around the world. It visits different states at different frequencies, and those frequencies are encoded by d pi. So remember, d pi is this visitation frequency for my policy pi. So this is the on-policy objective because you let the policy run in the world, and it's going to determine how frequently it sees some state, and then it'll do TD updates from that state. Okay, so the second term is the part where we do TD updates from that state, and d pi is telling us how frequently we visit that state. Okay, so on-policy TD, like I mentioned, obtains the minimum of this objective. And again, just to see if you're thinking a little bit, what do you think is the value of the minimum, by the way? So if TD went and got the minimum of this objective, what would it be? You don't have to yell it out. You can just think for 5 seconds, and then someone can yell it out if they want. Go ahead. Someone can yell it out if they want. Say it again. Yeah, 0, exactly. So I already told you earlier that our goal is going to be to make this equal 0. TD is going to actually go find the fixed point and is really going to make this 0. I only emphasize it because in some other settings, you'll write down an objective, and the minimum value may not actually, the minimum value may not actually be 0. The best thing you could do with that objective might be some number above 0. But here we'll actually be able to find this point that gets this TD fixed point. Okay? Okay, so now this is again the on-policy objective. So let's again think about what the possible choices are for the off-policy case. Okay, so the first objective I'm going to introduce is this excursions objective. So here, if you notice, the difference is actually that now instead of weighting by d pi, we're going to weight by d mu. And I sort of mentioned this earlier that we had these state probabilities that are induced by by the behavior policy mu, and so now we're going to actually visit states according to some different frequency, but we're still going to do TD updates from those states. So there's still an expected value under pi for the second term. Okay, and in practice what that really means is that, of course, we're going to be visiting states according to mu, and we're going to be taking actions according to mu, and so we're going to be using importance sampling to actually get a sample from this excursions objective that we care about. Okay, and then again, this is going to give us this off-policy TD algorithm that I mentioned to you earlier. So we're going to write down this excursions objective. If we were to try to go minimize it, we could use something like this off-policy TD algorithm. I haven't told you yet if these algorithms are sound, but I'm just saying you can go ahead and try to use something like off-policy TD. Okay, an alternative, though, you could say is, well, I don't really want my objective weighted by d mu. I want it to be like I had actually run my policy pi in the world so that I didn't ever have to be in the off-policy setting. I want to pretend that I ran my policy pi. So I want to go ahead and tackle the original on-policy objective. So I'm going to call this the alternative life objective. And now what that means is I actually have to correct both for the action probabilities and I have to correct for the state probability. So I have to go take that d mu. D mu actually tells me how frequently I am seeing states. And I have to go make it as if I had seen states according to d pi. Okay, so really the only distinction between these two things seems very small. You move from a d mu to a d pi, but it's going to have some important impacts. But first, anyway, let's talk about how we would do that. So how's the algorithm going to look different if we wanted to use the alternative life? And I hope that's sort of clear why it's called excursions and alternative life. For the excursions model, your behavior policy is running around. You're okay with the fact that it decides what states it's going to visit. And now you're just going to ask, well, what would I get if I were to take an excursion from where my behavior policy is? So you really just care about what are my values when I take excursions from my behavior. Alternative life is saying, I don't care what the behavior policy is doing. I wish I had an alternative life where I really got to execute this policy. Okay, so how are we going to deal with the alternative life setting? Okay, so now we don't just get to correct for my immediate action was different than my behavior policy. You have to go all the way back in time and say, I would have taken a completely different trajectory than my behavior policy would have taken. So I see an S1 all the way to Sn plus 1, and I want to ask how likely would I have seen this sequence under my policy pi? So we can just write that down. That's very straightforward. So the probability of this entire trajectory given policy pi is just the probability of doing all these transitions and taking actions according to policy pi. Hopefully that's clear. Okay, and then when we know how likely the entire sequence is under policy pi, so then we can just important sample the entire trajectory. So now the sequence was actually generated by mu. We need to remove the fact that the probability is under mu. So again, we're going to divide by this mu, and we're going to multiply by pi to make it according to the probability that we had actually followed this trajectory under policy pi. Okay, so now since we're importance on this entire trajectory, you can sort of look at what this formula is if you replace pi and mu. The p's are all going to cancel. You have no control over the dynamics of the world. So they're all going to share the same probability of S2 given S1, A1, and probability of S3 given S2, A3, S2, A2. So those are all going to cancel on the two of them, and you're just going to be left with pi of A1 given S1 divided by mu of A1 given S1, and pi of A2 given S2, and mu of S2 given A2. So those are really just the products of all these important sampling ratios. Rho of A1 given S1 all the way to rho of AN given Sn. Okay, so we know how to importance sample the entire trajectory, and that's going to give us what our alternative life algorithm is going to look like. Now, when we come to a time step t, we would like to do our update, our TD update delta t xt, but we have to ask how likely was it that I ever would have reached this point to actually do this TD update. Okay, so I need to go back and correct for the entire trajectory up to this point. And so again, I'm going to incorporate these important sampling ratios. So this product notation is just writing explicitly what I wrote down, implicitly what I wrote down there, where it's doing row 1, row 2, all the way up to row t. Okay? So it's really about how likely would I have been to get to this point to actually make this TD update. And if you correct for all those, then you're going to end up, it's going to be like you are sampling according to your policy pi, because you're seeing trajectories according to the distribution as if you had run policy pi. Okay. So those two algorithms, off-policy TD or excursions off-policy TD and alternative life off-policy TD, are minimizing these two different objectives, the excursion objective and the on-policy objective. And you might wonder how they actually differ in practice. So they look pretty different. One just has a row and one has a product of rows. But I sort of find it helpful to go through and think a little bit about what the updates might actually look like. So I'm going to show you this really simple little problem. It's this two-state MDP with termination into the state T. When you take action A1, you stay in S. When you take action A2, you transition to 1. When you take action A1, you stay in 1. And when you take action A2, you terminate. Okay, and the behavior policy is uniform random, so it's just randomly picking A1, A2, and the target policy is always going to choose action A2. I'll just keep this world here for now to see. So let's imagine the behavior policy, starts in S, that's the start state, and then takes action A2, it transitions into 1. So these arrows are just showing the sequence of states. So it was an S, then it went into 1, then it went into 1, then it went into 1, and then it terminated. Okay, so what that corresponds to is it took action A2, it took action A1, then it took action A2, and it terminated. Okay, so that's what the behavior policy did. Perfectly reasonable under the behavior policy. Remember, it's just randomly acting, so this is a possible trajectory under the behavior policy. So then we can look at what the importance sampling ratios look like for each step. Row 1 is 1 because the target policy, if you remember, always takes action A2. So probability of A2, oh, that's actually incorrect. I'm sorry, it should be 1/2. My mistake. So if row 1 is 1/2 because the behavior policy is random and the target policy is always going to take A2. Okay, and then we're going to transition to the next state, and the action is A1. The target policy never takes A1, so the importance sampling ratio is 0. The probability of A1 is 0 given any state. And then finally we transition into the state, and then we take A2. And again, I was wrong. The importance sampling ratio there should be 1/2. Okay? So I'm just going to remind you what these two updates look like. The alternative life is on the left, and the excursions is on the right. Go ahead, Rich. It's 2. Yeah, I just can't do more. Yeah, you're right. It's 2, 0, 2. Yeah, that's right. Hopefully that's clear to everyone. You would take it with 0.5, 0.5. So then 1 divided by 0.5 is 2. Even a simple example. Okay, so then the alternative life and the excursions, if you think about what would happen for both of these updates, what's going to happen? On the first time step, so t is equal to 1, they're both going to update the same, actually. They're both going to use this row 1 that's equal to 2, and they're going to do their TD update with that. Okay, on the second step, neither of them are going to update. The importance sampling ratio is 0. Your behavior policy, your target policy would never do that, so there's no way to infer anything about your target policy from what the behavior policy did, because you would never do that. Okay, and then on the last time step, only this excursions update is actually going to update because the alternative life has already seen a 0. So the behavior policy has taken a step that the target policy never would have taken, so it would never see this trajectory. So at this point, the product of your rows are going to be 0, and you're saying, I shouldn't do this update because this trajectory is not possible under my target policy. The excursions update instead is saying, well, I was already in state S3, I had no control over that, and now I can say something about what the value is when I take action A2, which is something I would do from state S3. Okay, so the target policy is able to get to state, is able to get to state 1, and so you can infer something about it from there, but it would not have gotten to it the way that the behavior policy got to it. Okay, so this example was sort of supposed to give you some intuition about why these two things would be different in a practical sense. The alternative life is going to be much more careful about actually updating this weight. If some trajectory is unlikely under the target policy, then you're just not going to be able to use that information. You're often going to be throwing away information. And the excursions update is going to not care about how it got to somewhere, and it's going to try to take as much advantage of saying, well, once I'm here, I can update towards my values. So really the consequences are, for the prior corrections, you're going to correct prior to when you got somewhere. So that's for the alternative life. When you include these prior corrections, it's likely going to be high variance because you're producting all these rows and you're also sometimes throwing away a lot of information. Okay, but it corresponds unbiased way to this on-policy objective. And if you only use posterior correction, so that means you're only correcting for the action probabilities, you're not correcting prior to when you got somewhere. So that's this excursions model. We're thinking it's going to be lower variance, that you're not producing a bunch of importance sampling ratios, and you're hopefully taking advantage of as much information in the world as you can. You can still say something about your value function from states using trajectories that are unlikely to get there. But it is definitely optimizing a different objective. So here I put it in brackets. You could say this is a biased objective. It's definitely different than the on-policy objective. So here we might ask ourselves, is this the same as saying that's biased or that it's a different objective? Nonetheless, it's definitely optimizing something different. And if you want the on-policy objective, it's not doing that. Okay, good. We reach another exercise that I think is sort of an important one. Okay, so there's a reason for this exercise. This is sort of a really difficult exercise, given what I have told you so far. But I would like you to do this one anyway, and I'm going to explain to you some of the answers to this exercise. And I think it'll be more obvious to you what I'm saying once you've thought about it a little bit. Okay, so the point of this exercise is to think a little bit about, I've shown you this excursions objective, I've shown the alternative life objective. I've told you a little bit about if you were to extract off-policy TD algorithms from those, what those two things might look like. Say one's high variance, one's low variance, and one's biased, and one's not biased. But let's not think about the algorithms for a second. Let's just think about the objectives themselves. So we have the on-policy objective on the left and the excursions objective on the right. Now, which one of these two might you prefer if you just had an Oracle algorithm that could solve these objectives for you? So let's not worry about variance issues. Let's just see, well, how do these solutions differ? Okay, which I didn't tell you really much at all on the last slide. Okay, so the way to sort of start thinking about how are the solutions different between these objectives is to sort of think about how might they be different under different function approximation settings. And the reason I want you to think about this question is that on the last slide, I sort of said, you know, it depends on which objective you care about. So I sort of want us to start thinking about which of these two objectives should we care about. Okay, so here when I say a tabular setting, I've still written this regular linear function approximation. So in linear value function approximation, we can always do the tabular setting by setting the features to be indicator features, where the length of the feature vector is the number of states, and you just put a 1 in the state index. So state 1 is 1, 0, 0, 0, state 2 is 0, 1, 0, 0, 0. Okay, if you think about it a little bit, you'll realize that that actually reduces to the tabular setting. Okay, and then you can think about a couple other settings. You can imagine a setting where I've given you really awesome features that correspond to some powerful function class. Okay, those are sort of vague words, but it's just going to leave them there for you to think about anyway. So imagine a setting where you have expressive features which correspond to having a powerful function class for your value function. Let's say your value, you can actually represent the true value function. Your features are so awesome. And you can think about a limited function class setting where I've given you really terrible features. Maybe it's just linear in the observations. And you cannot represent your true value function. Okay, again, I'm going to give you 3 minutes. Maybe turn to a different neighbor this time, I think that's what I wrote there, and talk to them about what you think what the differences would be. I will emphasize this is a hard question, but still think about it. Okay, I'm going to have to cut you off again. Hopefully it was a useful discussion and you made some headway or talked about something interesting in either case. Okay, so I'm going to talk a little about the answer to this exercises, and really the goal is to sort of think about when would you prefer one or the other of these objectives, because they really are different. Okay, first I'm going to start off by telling you that they're sort of the same in the tabular case. Now, not just sort of, they are the same in the tabular case, and it's going to start mattering outside the tabular case. Okay, so I'm still just going to keep these two objectives here so that you don't have to remember what they look like, and I'll remind you that the only difference is d pi and d mu, and those are telling you what your visitation is under pi and what your visitation is under mu. Okay, so in this case, x of s is an indicator vector, and what that means is if we want the expected value of pi delta times x of s to be 0, this can only be 0 if the actual expected TD error is equal to 0. Hopefully this makes sense. So in an indicator vector setting, you're going to have, like, you know, for example, 1, 0, 0, 0, and then so in order to have the actual vector equal to 0, that means you actually have to have the scalar multiplying out in front equal to 0. So the expected value of the TD error actually has to be 0. Okay, so there's no notion of sharing any information between the features. First feature completely independently has to get its TD error, expected TD error 0. The second state has to get its expected TD error 0, so which corresponds to the feature. Okay, and so what that means is that the on-policy and excursions objectives are both 0 if and only if this expected value is equal to 0. So they're both going to be 0 under the same conditions. Okay, so hopefully that makes sense. Here, you're going to have this vector of values that I told you about that correspond to the size of the feature vector, which in this case is the number of states. We want that whole thing to be equal to 0. And the weighting by d pi or d mu has no relevance. It's either going to be multiplying by some non-zero delta, or it's going to be multiplying by a 0. And it has to be multiplying by a 0 to actually get it to equal to 0. The only caveat here, of course, I should add is it's possible that there are some states that mu or pi don't visit, so they themselves are 0, so maybe you don't care about their TD error there. But I'm just going to assume here that that's not the case, that they're both covering the same sets of states. Okay, so in the tabular setting, it doesn't really matter which of these two things we chose, and actually that sort of impacted a little bit what we did with off-policy algorithms for a while. Now, what happens when we start moving to other settings? So is there going to be an impact of weighting for the other settings? Okay, so hopefully even just thinking about the tabular case sort of started getting you thinking a little bit about what does the d pi and d mu actually do in our objective. What they're going to do is they're going to upweight or downweight how important we think our expected TD error is in a specific state. So if d of s, for example, is high in a state, then that's going to contribute more to our error. And so we want to make sure that we give it a little more importance in terms of minimizing the expected TD error. If the d is really small in that state, then maybe we don't care too much. So if mu visits some states much more frequently and not other states very frequently, then we're going to focus more on getting our TD error low in this part of the state space and less in another part of the state space. And if there's a mismatch between d pi and d mu, then they're going to have different preferences between which states they give higher or lower preference. Okay, so if you think a little bit about how the d pi d mu gives some states higher or lower preference, then you can start thinking about what does that mean if I have a good function approximator and I have a bad function approximator. I still have used good and bad, but really what I mean is that you can represent the value function or maybe you can't represent the value function well. And there's other things that make a function approximator good or bad. Okay, so what's the impact if you have good features? Maybe this is starting to get a little more obvious what the answer would be. If you have really good features and you can represent your value function, this weighting should have less impact as well because you're not going to really need to trade off as much accuracy between states. So even if you care more about state 1 than you care about state 2, you can get both of them really accurate. So you're not really needing to trade anything off. You're still going to get a really good value function, whether it's weighted by d mu or d pi. There's always going to be a little bit of error. So if there really is a big skew, you might still end up skewing your value function, but it shouldn't matter as much. As if, for example, if you have a really limited function class and now you really have to make hard choices. Am I going to focus really well on getting my value function accurate in this part of the space, or am I going to sacrifice this part of the space to get the value function accurate in this other part of the space? And really sort of the third setting is a little bit more the setting we think we're going to be in. We're not really in a tabular setting. We're not going to have amazing function approximaters. We're always going to have to trade off some accuracy. So the choice of between d mu and d pi, if they are different, is going to impact the final solution. Okay. So that's just about the objectives. That's not even about the algorithms optimizing those objectives. Then still the next step is, still which one is the better solution. It's still not obvious that you should weight by d pi or d mu, but just note that they are different. I would say it still remains sort of an open question about which one people think is important. I'm preferential to the excursions objective. Okay, so what have we talked about so far? I sort of told you a little bit about why off-policy learning is important. We've talked about the different objectives that we could consider, and really these are sort of the two key objectives that we could consider, weighted by d mu or weighted by d pi. So thinking a little bit about what the different weightings are in our mean square projective element error, and that can actually matter. And before I continue on to the last thing, which is actually what the algorithms are going to look like, do you have any questions so far about these two things or anything else that I've said? Still following all the notation? It's clear what row is? Okay, go ahead. Yeah, at the back. Okay, what does it do to your variance? So there you're starting to think a little bit about what happens when we actually try to optimize these objectives if your behavior policy doesn't do something that your target policy would do. Let's start talking about the algorithms then, and maybe you can ask me that question more as we start talking about the algorithms. Okay, good. So I guess everything is crystal clear. Okay, let's talk about the algorithms then. Okay, so I've sort of shown you a few very simple algorithms. On-policy TD, the excursions off-policy TD, and alternative life off-policy TD. And I haven't really told you about what their properties are, sort of alluded to them a little bit. So a natural question is, do these algorithms actually converge? And do they converge to what we want them to converge to? Okay, so again, Amir has really talked a lot about convergence, but I'm just going to remind you sort of what I mean by convergence. What we'd like to say is in the limit of updating, I've given you all these update rules. WT plus 1 is equal to WT plus alpha times some update. So if you pick step sizes appropriately and we do these updates, the limit of updates says WT eventually get to the optimal linear function approximator for the objective that we have specified. Okay, so that's sort of what our goal is for convergence. And here I'm still talking about linear function approximation. So we were thinking about our weights converging. Okay, and underlying TD is a projective Bellman operator, again, sort of mentioned and alluded to earlier. I'll show you a little bit more why that's true on the next slide. And so we kind of have to think a little bit about two things that naturally come up when we start thinking about off-policy TD. One is, do we have to think a little bit about what the behavior policy is doing? So we're probably going to have some requirements in our behavior policy. And of course, we're going to have all this regular standard requirements on our MVPs and things being ergodic and stuff. But we might start thinking a little bit about requirements on behavior policies and requirements on the operator. Because the TD update does have a projective Bellman operator. Okay, so for the behavior policy, you might imagine that some things are important. One thing we're going to usually assume is that the behavior policy is fixed. It's going to be a little bit more complicated if it's changing. We'd like to think about a fixed behavior policy. And then another thing is that we'd like to make sure our behavior policy actually takes the actions, at least sometimes, that our target policy would take. Okay, so if we're in a state and from that state our target policy would take action A1 and our behavior policy would never take that action, then we just cannot learn anything about that target policy in that state when it takes that action. So it's hard to say that our weights are necessarily going to converge to the optimal value function approximation if we don't see the data that lets us actually get to that point. Okay, so really that's kind of the requirement. And again, Miramasood really hit this home for the operator. We really need it to be a contraction, because if it's an expansion, then we're just going to diverge off. We need to actually converge to a fixed point solution. So we usually make nice standard assumptions that we can actually satisfy the first one. But the problem in off-policy TD is that the second one is no longer true. So the operator is not going to be a contraction. Okay, so the answer to the title of this is off-policy TD does not necessarily converge. Okay, so let me just remind you briefly what projective Bellman operators are and sort of how this relates to TD. Okay, so I'm just going to draw this slightly different picture and remind you what this is. So here our function class F is going to be this class of value functions that are linear functions. So sticking in that case, I'm just going to write it more formally here. And when we're using our Bellman operators, we might start with some value function V. It's in this space, this plane, that is defined by the space of all possible linear value functions. So here it has X to be the features X, and D is going to be some weighting that also defines the space of your possible value functions. Okay, and then we're going to apply our Bellman operator T times V. That's really just taking V and doing R plus gamma times P times V in order to give us this next point. Okay, and then when we actually apply that operator, that may be outside of the space of things representable by our value function, so we're going to have to project back down. And here this projection operator is subscripted with F to indicate that, of course, the projection is relative to the function class that we have. Okay, and then we're eventually going to be left off with this. The difference between where we started with V was going to be compared to this projected Bellman operator applied to our V. Okay, that's going to be mu-square projected Bellman error. Okay, that was just sort of a little recap. Okay, so that was just a recap of what Bellman operators look like, but how does this actually relate to TD? So I sort of mentioned this earlier, but I just want to mention it again. When we write down this expected value under pi of the TD error, this delta is, the R plus gamma P pi minus, R plus gamma V of next state minus V in this current state. And then we actually expand out this expected value. You can actually write it as Bellman operator applied to V. Here I've subscribed with W to indicate that the parameters are W. And when we do T times V, that's going to actually give us a vector of values, one value for each state. So then I'm going to index by state S to tell you that that is the value from state S. Okay, so that makes sense. Okay, so that's sort of how the two things are related to each other. We're used to seeing the TD error in the TD update, and when you take this expected value, it looks like this Bellman operator indexed at a particular state. Okay, and of course, when we are doing TD, we're always keeping within our function class. So when we look at this expected TD error and we apply our Bellman operator, like I said, it may not be representable, so we're going to have to project back into our linear function class. And then our mu-square projected Bellman error is going to look exactly like this. So it's going to be take your T times V. It's no longer maybe a linear function, so you're going to have to project it back into your linear function class and compare it to what you previously thought your value function was. And maybe if the projection operator is not that obvious to you, you can think about one way that you would go outside of your linear function of class by thinking about the reward function. The reward function may not be a linear function of the features that you have given your agent. And so if it's not representable by your features and you apply this Bellman operator, it's possible that you can no longer represent it with those features. Okay, so you really are outside of the space of things representable by your class, and you're going to have to project back down into your class. Okay, so in the end, TD is really trying to minimize this mu-square projected Bellman error, which is trying to take advantage of the fact, I don't know which is, it's only on my screen. Oh, okay, sorry, my screen is just blinking. I'm just going to look at this one. The mu-square projected Bellman error can also be looked at this way, which is just saying, try to minimize the difference between the projected Bellman operator applied to V and V. Okay, so we really do care about what the properties of these Bellman operators are for TD because underlying TD are these operators. Okay, if you miss most of that, it really doesn't matter. The conclusion that matters is the Bellman operators matter for TD. Okay, so what does this actually mean for convergence? When we start thinking a little bit more about what the Bellman operators are, in the on-policy case, so when D is equal to D pi, so the mu-square projected Bellman error when D is equal to D pi, and we have this projection operator where D is equal to D pi, then we know that this projected Bellman operator for linear value functions is a contraction. So on-policy TD converges. We all love on-policy TD and have been using it for a very long time. But unfortunately, if you set now this D to D mu and our projection is defined in terms of a D mu, this operator may not be a contraction anymore. So in fact, it's going to be, in some cases, it's going to be an expansion, and actually each time you apply your Bellman your projected Bellman fixed point operator, it's actually going to start spiraling your weights out of control, which is bad. So we're not going to be able to converge when we use these projected Bellman operators. Okay, so really the conclusion from that is that our excursions off policy TD can diverge. And there are nice counterexamples for this. And really the reason is due to the fact that this expected update underlying the TD update, which is the projected Bellman update, is itself not a contraction. Okay, so that's sort of unfortunate. We had these sort of two options. We could have done an excursions off policy TD, and we could do alternative life off policy TD. We weren't really that interested in doing the alternative life, which sort of looked high variance. So really, what are we going to do? And this kind of leads me into a little bit of a story where I feel like this is sort of what happened to the field, actually. There were some counterexamples given. Off-policy learning looked like this really difficult thing to tackle. And then there was a flurry of activity afterwards, I would say, to start really getting a handle on how we should solve this problem. So really kind of start off with, off-policy learning is this really important thing, and there's all these things we really want to be able to solve this problem. So the promise of Q learning was great. The promise even of excursions off-policy TD was maybe great. The idea is you can just generate policy from some other behavior policy. So you can generate data from a behavior policy, and then you can learn the optimal policy for other tasks, or you can just learn about other policies. That is actually a really exciting thing to be able to do. But then, we started understanding some of these divergence examples, particularly in the 90s. And then there was some successes in trying to deal with this problem using this alternative life TD. And alternative life off-policy TD, unlike excursions off-policy TD, does converge, because it really just goes and converts it back into this on-policy objective, and we have no issue with this dmu messing things up. Okay, so there's kind of this history where it started to realize that there's these divergence problems, and there was some proposed algorithms, but there's still issues. So we would like to keep using Q learning. People, of course, kept using Q learning because it's a great algorithm, but we have convergence counterexamples. And then in the sound algorithms that were getting developed, they really had these variance problems where there's a lot of these products of rows. So there's really these two difficulties for two reasons. And I kind of mentioned already the prior and posterior corrections. So without prior corrections, so without correcting for this dmu d pi, then we didn't get those contractions. But then we were stuck. If we added prior corrections, we had this product of rows, then clearly we're going to have a lot of variance problems. And in fact, there's some nice examples where actually infinite variance is not such an uncommon thing you'd expect to see if you had to use these prior corrections, where you correct it all the way back to the beginning of an episode. Okay, so there's these two problems. They sort of seem at odds with each other, but there's sort of been two really nice solutions towards trying to solve these problems. Okay, and so towards solving convergence without prior corrections, so on the last slide I mentioned, if we don't use prior corrections, it's bad. If we do use prior corrections, it's bad. So there's sort of been two different directions for how can we still do well if we don't use prior corrections, and how can we still do well if we do use prior corrections. And this is really these two families of algorithms. So convergence without prior corrections, the natural thing to do is say, well, the projected Bellman operator is not a contraction, so I guess we can't use fixed point solutions. Let's do what maybe we could have done a while ago and try to use gradient descent approaches on an objective function. And once the objective function was identified, this is maybe a more straightforward thing to do. Okay, and the other solution was to try to still do prior corrections, but to try to reduce the variance of those prior corrections. And the idea was to incorporate prior corrections into an excursions formalism. So that's what these algorithms called Emphatic TD. Okay, so I'm going to start with the first one, because it's sort of interesting why we've been using TD for so long and why it took so long for us to start using gradient descent to do off-policy evaluation. Okay, and again, the slide title sort of tells it all. There's difficulties in actually getting the gradient of the mu-squared projected Bellman error. So one difficulty I didn't mention is just, I think it took a little while to actually come up with this really nice objective. This objective function is really not that old. So the first time something like it appeared was maybe in 2008, if that's when the Antosh paper came out. But let me tell you why there's these difficulties. So I'm going to write for you once again the mean-squared projected Bellman error. Before I wrote for you this simplified variant, I'm just going to give you the more full variant here so that we can write out what the gradient actually looks like. Okay, so the first term on the right-hand side is still exactly the same thing you've been seeing over and over again, weighted by d mu. And I'm going to call that A of W. It's a vector of values. That's the size of the number of features. Okay, and I'm just parameterizing by W because clearly it's dependent on W because delta has a W inside it. The value function has a W. Okay. So in our objective functions, we're going to want to be clear about what has a W and what doesn't, because the W is the thing we're optimizing. Okay, and then we also have this covariance matrix that just tells you what is the covariance of the features you're going to see across your state space. Okay, so the mean-squared projected Bellman error is really just a quadratic loss. It's saying take this error that looks sort of like a squared error, and then you're just going to take the dot product between these two things. So this is really just a quadratic loss in terms of this A, weighted by some covariance matrix C. So it's a weighted quadratic loss. The previous variant really just omitted C. So if you just mentally omit C, A transpose A is exactly equal to this squared 2 norm that I wrote for you earlier. Hopefully that's clear. Whenever you take a vector like V transpose V, that's just equal to the square 2 norm of that vector. Okay, and here the C is really not very important. So if it helps, just mentally remove the C. Okay, so this is what the mean square projective element error looks like. Then we can take the gradient of this mean square projective element error. Okay, and again, I just went and did that algebra for you. The algebra is absolutely uninteresting, but it looks like this term. Okay, so we have a C inverse times an A times W, and then there's the gradient of A times W in terms of W. And right now, what that looks like doesn't matter. I'll show you what it looks like on the next slide. But I kind of want to contrast this with what this would look like in the supervised learning setting. Okay, so in the supervised learning setting, we might have a loss that looks like, for example, the expected squared error. We have some target y. We'd like to predict that target with some function, let's say still a linear function. So we're going to learn some weights, do x transpose w to approximate y. Everyone's hopefully comfortable with that supervised learning problem. Okay, and when we take the gradient of that objective, then, I leave out the gradient on the second line. I'm sorry. That's already me taking the gradient. If you take the gradient of that second objective, it just looks like this term, x transpose w minus y times x. Okay, so you're going to notice two differences between this. In the supervised loss, we just have one expected value. We're just going to go and sample that expected value. So we'll see an x and a y, we'll compute our gradient. We'll see an x and a y, we'll compute our gradient. This is not true for the mean square projective element error. This is actually the product of three expectations, if you'll notice. So the A of w is an expectation over all states. The covariance matrix is an expectation over all states, and the gradient of A of w, unsurprisingly, will also be an expectation. A sum over all states was an expectation. Okay, so when we want to actually sample this gradient to do updates, like gradient descent updates or stochastic gradient descent updates, we're going to run into this double sampling problem. Also, again, alluded to by Amir Masood. So the key problem here is that when you take the expected value of two random variables, an x and a y, it doesn't necessarily equal to the expected value of x times the expected value of y. Very foundational result. And so here, we're not going to be able to say on one time step, take a state, action, next state, and reward, and then just compute the products of these three things, because those will not be independent random variables. So we're not going to be getting samples of the first expected value, samples of the second expected value, and a sample of the third expected value. Okay, so here I already told you mentally you can ignore C. So really what we really want is independent samples of A of W and the gradient A of W. Okay, so, we have this objective, but now we start to sort of run into, it's a little bit more difficult to get gradients in this objective, but of course there's many awesome people in the community and there's different solutions that have been obtained. I'm just going to remind you that one solution actually was just to use least squares temporal difference learning, but it's a quadratic cost algorithm, so I'm just going to put that up to the side to tell you that that was an option, but we're going to think about how can we do this in a linear way. Linear in the number of features. Okay, so the strategy taken by gradient temporal difference learning, so gradient TD, is to try to estimate one part of this product of these expectations using a vector that's sort of just trying to track what the expected value is, trying to track the second part of this gradient of the mean square projective element error as an actual expectation, and then just sample one part of it. So it's going to try to sample the gradient of A with respect to W, and it's going to try its best to approximate incrementally C inverse times A of W. Okay. Maybe this seems like a difficult thing to do, but there's a nice convergence result that says, you can kind of track this H that's trying to approximate this term C inverse times A of W, and there's a nice update to do that. And then we can just pretend like that's the true expected value, it's the true second term, and then all we have to do is to get an unbiased sample of this gradient of A of W. And this term right here is exactly an unbiased sample of that. So the unbiased, here is just the feature vector on this time step minus gamma times the feature vector on the next time step, and then outer product with X transpose. Okay, and then when we actually product these things, the update to the weights is supposed to be the gradient. So we would take the unbiased sample of the gradient of A and multiply it by this second terms that are the expected value. Okay. I wasn't able to point at things. So hopefully that was clear how this broke up the expected value problem into try to slowly approximate some expected values and sample one expected value only, which of course we can do. Okay, so that's pretty cool. And so gradient TD, this is one algorithm. There's other algorithms that try to sample this gradient of the mean square projective element error in other ways. This is just one of the first algorithms that did that. Okay, and then since then there has also been this kind of cool other way to think about this problem where it actually ends up being actually exactly the gradient TD algorithm but interpreted in a different way, where first you take the mean square projective element error and then you're going to rewrite it as the saddle point problem where you have a min and a max. So in the mean square projective element error, we are trying to find the minimum W, but we can go ahead and rewrite it in this way because it has this nice, you can just trust me. You can write it in this way where we could have written the mean square projective element error as find the H that's the max H for this. So you want to make H transpose A of W as big as possible, which would make you want to put H be as large as possible all the way into infinity, but then we're going to subtract off the L2 norm, which is not going to let H get too large. There isn't a whole lot of intuition behind this, except for the fact that the solution to this is exactly the H I wrote on the previous line. Okay, so you can think about this problem in this way, but once you write the mean square projective element error as this saddle point problem, we no longer have products of expectations, if you notice. You're trying to solve for some parameter vector H. You don't even really have to think of it as approximating the C inverse times A of W. And then we just had this A of W in here, if that makes sense. Okay, so we've kind of replaced a bunch of the mean square projective element error with this extra variable. And sort of the nice thing with the proximal methods, why I think they're an interesting idea, is that it lets us take some more of the understanding from optimization, where they're great at optimizing saddle point problems, and we can start bringing them into reinforcement learning in a more straightforward way. Whereas less people have worked on the, what do I do if I have products of expectations? How can I get a good sample of that? Okay, so just here for reference, if you're interested in what other algorithms exist, there's sort of these two classes I've already mentioned, GTD, where you think about, I need to estimate these two expected values, and I'm only going to sample one expected value. I'm going to call those two time scale approaches, because they use the two time scale analysis. And so there's several of these other methods that use that strategy. There's another algorithm called TDC that samples in it a different way, and really is the variant of GTD, gradient TD, that we often use. And some of these other really nice new results using this algorithm called ABQ that tries to remove some of the important sampling ratios. Okay, and then at the same time, of course, there's been people working on the saddle point problem. So there's this nice paper about taking some of the stochastic variance reduction strategies from stochastic gradient descent, from the literature on stochastic gradient descent, and bringing that into reinforcement learning. Sort of a standard being able to bring it in, again, once it's formulated as this saddle point problem. And then this new paper at ICML this year about gradient tree backup and gradient retrace. Okay, cool. Okay, so that was one set of algorithms. So that was towards the problem of, I'm not going to use prior corrections, so my projective element operator is not a contraction, so instead let's try to get the gradient of some objective, and that gradient was the mean square projective element error. Okay, the other direction was, well, I'm still going to use prior corrections, but I'm going to try to make it lower variance by incorporating it into the excursions model. Okay, so that's exactly what emphatic temporal difference learning is doing. Okay, and the way that it incorporates it into the excursions model is that instead of saying, I'm going to apply prior corrections so that I could have had an alternative life. So I can imagine what would have happened if I had run policy pi from the very beginning of this episode. If you incorporate them into the excursion, what you're saying is, I started my excursion, let's say 10 steps into the episode, and then I imagine starting to run policy pi. I only need to correct since I started that excursion. So I'm going to incorporate prior corrections, something like prior corrections, but assuming that I'm actually taking excursions from my behavior policy mu, not since the beginning of time or since the beginning of an episode. Okay? So this is sort of trying to mix the two. It may be a little bit confusing at first when you hear it. But it's going to give us a different weighting than d mu and d pi. It's not going to give us either of these things, but it sort of gives us something maybe a little bit in the middle. So I'm just going to write down a little bit what this emphatic weighting looks like and maybe give some intuition about it. Okay, so what would it mean to do prior corrections from an excursion? So it still means that your state visitation frequency is going to be according to d mu. So your behavior policy is still deciding what parts of the state space you're going to visit, but now once you say, like you imagine that you're going to do an excursion from that state, you're going to let your policy run for a while, and then you'd like to go back and do prior corrections starting from that excursion. So here, if you look at what this f of s is going to be this different third weighting, so not d mu, not d pi, but a different weighting. It still always has a d mu in it, but now it's going to say, okay, I started in some state s prime, and now I'm going to look one step back, or I'm currently in some state s prime. I'm going to look one step back. I'm going to discount by some gamma, and I'm going to look at what the probability would have been that I had taken this action. Okay, so actually probably the most intuitive way to look at this, I'm sort of running a little bit out of time. Probably the more intuitive way to look at this is to look at the actual algorithm itself, and otherwise I very much encourage you to go read the Emphatic TD paper, which explains this very well. So if you look at what the actual algorithm is doing, you look at this FT, which is trying to approximate this F of S, or get a sample of it. Okay, so what it's doing is taking the previous value of FT and is downweighting it by a gamma and a rho T minus 1. Okay. So then when we actually do this update, before we were either waiting by a rho T to do our one-step update, or we're waiting by a product of rows all the way back in time to look at our alternative life update. And now FT here is sort of replacing what that product of rows all the way back in time was. It's not a product of rows all the way back in time, but it does actually accumulate these rows downweighted by this gamma, and it'll actually be cut off depending on what the gamma is going to be. Okay, I'm not explaining this very well. So it doesn't actually exactly correspond to a prior corrections method within the excursions model. It's sort of giving you an approximation to that. So this weighting by gamma is maybe not as intuitive. But in the end, what you are going to get is something that looks like a d mu, and then with a weighting that tells you if I were to run my policy pi, what would be the sequence of states that I would see into the future discounted by my gamma. So I care more about states that I'm going to be visiting now immediately from this excursion, and I sort of stop caring as much about my visitation frequency as I go further into the future. Okay, so this is a little bit more of a practical thing to do than to correct an entire trajectory fully. It's caring a little bit more locally about where we're starting that excursion from. Okay, so what you would hope that instead of having this product of rows all the way back in time, we're having this thing that's going to be a little lower variance because we're not producting back as far, and we're actually discounting with this gamma as well. Okay, and what I should actually emphasize here then is if you actually incorporate these pseudo prior corrections in the excursions model, now again we get to have a projective Bellman operator that is a contraction, and we do get to have an off-policy TD-like algorithm that is convergent. Okay, cool. So the last thing I said that I would mention, actually this is the second last thing that I'm going to mention, is this whole thing has been about linear value function approximation. Okay, and so really a natural question I think for many people is, what does this actually mean for nonlinear function approximation? Maybe you'll go take some of these off-policy algorithms, and then you're going to want to use them with your neural networks. Okay, so one thing I want to emphasize first is we talked about linear value function approximation, but that doesn't mean we talked about poor value function approximation. You can actually have really powerful value functions if you can construct really good features. So really the whole talk has been about if someone handed you a really good set of fixed features, you could just go ahead and apply all the algorithms we've talked about so far. So you could train your large convolutional neural network on images, and you could get really useful features that describe your images, and then you could hand them to your TD algorithm if that was of interest to you. So this by no means linear doesn't mean linear in your inputs. Okay, good. Okay, now for nonlinear functions, of course, things aren't just going to transfer that easily. So there's sort of, the key thing that sort of is different is, well, actually I guess there's two key things that are different, but one of the most important ones is that the mean square projective Bellman error is now going to look a little different. So the nonlinear mean square projective Bellman error is a little bit more complicated, and this is because the projection operator is going to change. So the projection operator for linear value functions, or for linear functions, is a nice, very simple projection operator. And when you move to nonlinear functions, that projection operator starts to look, can look very terrible. Okay, but one thing I want to mention is that even though mean square projective Bellman error is going to be a little more complicated, there are actually algorithms that do tackle the nonlinear mean square projective Bellman error, and maybe there could be more algorithms that tackle the nonlinear mean square projective Bellman error. But still, a lot of the understanding about what should our objective look like remains the same. So you still might want to ask whether it's nonlinear or linear value function approximation. Should I weight by d mu or d pi? Should I weight by this f, which we're calling the follow-on for the emphatic weightings? So still sort of understanding what would be the solution to my objective is going to be very similar if we're thinking about choice of weightings. Algorithmically, there are going to be some differences. Okay, I was going to give you this exercise, but actually before I give you this exercise, because we don't really have that much time, so maybe I'll leave it as a exercise at the end. I'm going to mention one, well, those are questions. So should I do an exercise for a couple minutes? And then, you know what, actually this is what I'm going to do. There's really no reason to do something like that. So what I suggest is I have these slides up. I'm going to put these slides up. I suggest that after thinking a little bit more about off-policy learning, these could be questions that you would find fun answering for yourself. Okay, so again, going back to when might you use off-policy learning, if you were to start running it in some system you have, what choices would you actually have to consider? And what properties would you actually care about for your algorithms? You know, maybe you don't care that off-policy TD diverges. So maybe you could start thinking about what you would actually do if you were to use off-policy learning. And also, if you were to start tackling the nonlinear function approximation, how does what you have sort of learned here impact what choices you're going to make for that as well? Okay, so I'm going to leave about 5 minutes for questions, but I have one last thing that I wanted to mention that I sort of think has nothing to do with anything I just talked about, but I sort of think is just an important clarification point about off-policy learning, since this is an educational lecture about off-policy learning. So there's these other additional topics that I really didn't get a chance to get to. I'm just going to mention the first one, but I didn't talk at all about extensions to eligibility traces, and it gets a whole lot more interesting when we have eligibility traces, because now the eligibility traces themselves actually have products of rows in them as well. And I also didn't talk at all about the control setting and things like off-policy gradient methods when we want to do off-policy control. Okay, there's a lot of interesting things for those two topics as well. And yeah, I just might call to talk to you about them. Just to tell you that we do care about it. There are things about off-policy learning for policy gradient methods, and we do have eligibility traces in our off-policy methods. So you can go look at the papers to find that. Okay, so this last very off-topic thing to talk about is that there is one other area called off-policy policy evaluation that is sort of a different area, where the goal is, rather than to try to find the value function of a policy, the goal is to get the value of a policy. So here I'm writing V of pi, sort of overloading notation for V, but making it lowercase, where the goal is to say, this is particularly for real scenarios where you generate data from some behavior policy and someone actually has proposed another policy, and you would really like to know, how good is this policy? I want one number, maybe so I can present that number to my boss, and then I can tell my boss, hey, look, this number is larger than the previous number, and they might actually run your new policy. Okay, so the goal here is just to get this single number that tells you across the state space with some weighting D again. Again, that D is always going to be an important choice. Look at the weighted sum of all the values across my state space, and that's going to give me an idea of how good my policy is, summarized into one number. Okay, so the setting is still otherwise the same. The data is generated by some behavior policy, but we don't necessarily actually have to estimate the value function v pi to estimate this specific scalar quantity. Okay, so it's really, like I said, sort of orthogonal to what I've been talking about, but I just wanted to mention that if you go on and you start reading about these things, you're going to find off-policy policy evaluation papers that care about this problem, and off-policy policy evaluation papers that care about learning the value function. And they're two different things. Okay, I think that's all I wanted to, that's all I wanted to say. Keep this. Okay, I'll leave this slide up, and then we can. I think we have 5 minutes for questions. Go ahead.
So a lot of times we make claims that off-policy algorithms are more sample efficient, but do you know if there are theoretical results that back up that claim? That
let me hear what you said again. You said they are more sample efficient. Is that what you said?
Yeah, as in like they are sample efficient
compared to, say, on-policy algorithms. I think that I'm just going to guess what you mean by that distinction. I'm going to guess the reason people say that one would be more sample efficient than that off-policy would be more sample efficient than on-policy could really only be two things. One is that they're imagining they have a batch of data, which is off-policy, and if they had to be on-policy, they couldn't take advantage of this data. And so then they're going to be less sample efficient in that way, because there's just a whole amount of data that they're not allowed to take advantage of. Okay, but if you had a batch of off-policy data or on-policy data to, say, estimate your value function, it's not clear to me that one would be more or less sample efficient. And really the intuition has been on-policy generated data should be maybe more informative for estimating your value function. You may also be thinking about control, where, again, you want to be able to use previous experience. They do something like experience replay. And if you can do experience replay and take advantage of this older data for control, then again, you just get to have all this more data to help inform your policy. So I'm not sure if I would exactly say one is more sample efficient or the other. It's about how much data do I have access to. So again, it's different than sample efficiency, because sample efficiency is more about, for a small number of samples that I have, can I extract as much juice out of those samples as possible, rather than distinguishing between I have a bigger data set or I have a smaller data set. Did that answer your question? Okay. Yeah, sure, go ahead.
So divided these two classes of emphatic method and also this
Right.
classes. So this new work, retrace work, do you categorize it in the second category, like the emphatic methods, or is a separate category?
Yeah, there aren't that many emphatic algorithms. So the retrace methods, the non-gradient-based retrace methods, are really sort of in the same category as off-policy TD. And actually, the archive paper, so we're going to highlight that it really is like an off-policy TD algorithm that sets the lambda parameter a particular way in the eligibility trace in order to keep the variance low. So they're really sort of off-policy TD methods that try to keep the variance low, and have only been shown to converge in the tabular case. But I'm just going to scroll back to this. The one paper I listed here that's called Gradient Tree Backup and Gradient Retrace, that was just the ICML this year, is sort of taking those algorithms, turning them into their gradient forms, using this like saddle point formulation, and then giving the form of retrace that is convergent, and then it is really just of this form, like it's one of the mean-square projective element error algorithms.
So it's more like the emphatic algorithm, right?
It's not like the emphatic algorithm. I don't think it's like the emphatic
Okay, so
algorithm.
you categorize it in the first group?
Yes, yeah, I would categorize it in the first group.
Okay.
You go ahead.
So everything right now was on a fixed behavior policy, but how far does it break if we can have time-varying behavior policies?
That is a great question. So let me say, I don't know of a lot of papers that are actually dealing with varying behavior policies. I believe there are a few. I haven't thought about it enough when it comes to time-varying behavior policies. But my instinct is to say it shouldn't really matter that much, particularly if it's something like an excursions objective. So in an excursions objective, you really do care more about, given I'm in this state, I'd like to correct for my updates from this state. You've already sort of given up a little bit maybe on controlling so much the state visitation frequency. So what's going to matter more then when you have a changing behavior policy is the fact that you're going to have a changing visitation, like a state visitation frequency. But I would still say that there's not a whole lot understood of exactly what happens when the behavior policy is changing. I'd be happy to be wrong if someone else here knows about new work about what happens when you change the behavior policy. Or if you do know and you don't want to raise your hand, come talk to us at the end. Oh, I think we're over time, actually. Oops. Okay, thank you.